In this problem, we are told that we need to find the Norton equivalent circuit with respect to our terminals A and B. We need to find the current flowing through here, we need to find our ZT of H, and then we will have this problem. Well, we don't need a source charge in here because we are given a current to the right of it, which is this part right here. So we are going to be using this for our entire equation. If we look at section 4.9 with source transformation, what we are going to do is take this current and take this resistance and make it a voltage on the left side and then bring the resistance up here. Since this impedance and this impedance, a inductor and a resistor, are in series, we can just add them together. From this, we are going to get 15 plus J30. And then once we move this, because we know that we are going to have this resistor here, and then our inductance and our resistor here, this is also going to be in series. So we're going to add our 25 to it. So from this, we are going to have a resistor right here, and for this resistor, it's going to be 40 plus J times 30, and that's because we add all the impedance together. And now we are going to have our voltage on this side per the source transformation. To find our voltage here, we need to set it equal to our current times resistance. We know that our current is 16 with an angle of 0 degrees. We know that our resistance that's tied to it is this 25 ohm resistor, so we're just going to multiply this in. This is going to give us 400. So our voltage here is going to be 400 with an angle of 0 degrees. When we factor our 25 in, we don't factor it into our degrees. We only factor it into our first part, the magnitude. Now we have this here. From this, we are going to convert this back to a current using this voltage and this new resistor right here. From this, we will have our resistor in parallel like this. We're still going to have it be 40 plus J times 30, and then we are going to have our current flowing through here. Now to find our current, we are going to use an Ohm's law where we set our current equal to the voltage over our resistance. And we know that our voltage is this 400 with an angle of 0 degrees, and we know our resistance to be this 40 plus J ohms. So we are going to put these over each other. Now looking at section 9.10 extra, we need to use division here. To use division, we need both of these to be in the phasor form where we have a degrees. So this bottom part right here needs to be converted. To convert this, we are going to have our Vmax equal to the square root of our first value, which is 40 squared, plus the next value, which is 30 squared. And then we're going to have our theta equal to tangent -1 with our imaginary number, the 30, over our real number, which is the 40. And then we're going to find both of these and plug them back into the equation. From this, we're going to have that our I is equal to the 400 with 0 degrees all over 50, and then we have our degrees of approximately 37. Now looking at this, we are going to divide the real numbers, and then we are going to subtract the top from the bottom of our angles. From this, we are going to get that our I is equal to 8, and we're going to have a negative 37 degrees. This is our phasor form. However, it asks for us in rectangular form, so we need to convert this back. We also know that it's our I of n because after we combine these two resistors, which will have no effect on the current, we are going to have the Norton equivalent. Now to convert this back, we are going to have our number, which is 8, outside, and then we're going to have cosine times our angle, which we know to be negative 37, plus j times the sine of our angle, which is negative 37 degrees. From this, we're going to get approximately 6.4 plus j with a negative 4.8. And we're going to write it in here like this. And this is the answer for our I Norton. Now we need to find our ZT of H. So we're going to set ZT of H equal to ZA of B, because this is the resistance. And we know resistance is equal to voltage over our current. We found our current, so we can actually use this in our equation. However, we don't actually need to, because we can just make our V equal to our I of R, because we know V is equal to I of R. And if we set V equal to I of R, our I's are going to cancel out, and we're just going to be left with an R right here. So our answer for a ZT of H is equal to R. Now we just need to find R. We can see that we have this resistor and this capacitor, which is an impedance, which is kind of equivalent to a resistor, in parallel. So we're going to have to use the parallel form for this. We're going to have 1 over our first impedance, which is 40 plus J30, plus 1 over our next, which is negative J50, and this is raised to the negative first power. Now, if we have two capacitors in parallel, we'll just add them. But because we have a resistor here, we are going to override this because the resistor takes place first, and that's why it's in parallel. And that's why we're using this formula instead of just adding them together. From here, we are going to multiply the top and bottom by negative J50, 40 plus 30J. If we do this, we are going to get negative J50 plus 40 plus J30, and this is all happening over negative J times 50, and then in parentheses we're going to have our 40 plus J30, and then this is all surrounded by negative 1. From here, we're going to combine like terms. We can see that our negative J50 and J30 are going to add together. This is going to give us a J20, a negative J20, and then we have a 40 out front. So we have 40 plus J with a negative 20 inside. And then if we factor in the negative J50, because it's out front, we are going to have a 1500 if we combine our negative J50 and J30, because if we have two J's, that means it's an imaginary number, and a J is equivalent to the square root of a negative one. That's what the imaginary represents. Well, if we have two square roots, it just makes the actual number. And if we do this, we'll have a negative 1. So this will cancel out the negative in front, leaving us with just a 1500. Now, if we multiply this into our 40, we're going to get a negative J 20,000. And since we have to invert this because of this negative 1 right here, all we're going to do is move the bottom or the top and just switch its location. Now the bottom will be on top and the top will be on bottom. If we look at section 9.10 extra in the notes, to do division, we need this in the phasor form. So we actually need to convert this. And remember, this is equal to our resistance. So once we find this, we find our answer. I'm going to look at the numerator first. So when we need to convert this to phasor, we are going to have our Vmax equal to the first part, which is 15,000 squared, plus the next part, which is negative 2,000, and this is also squared. And then to find our theta, it's going to be equal to the tangent of negative 1 with our imaginary number on top, negative 2,000, and our real number on bottom, which is the 1500. And we're going to also do this for the denominator. From this, we are going to get these two values. So this is our denominator and this is our numerator. We are going to have 2500 with a negative 53 degrees over 45 with an angle of negative 27 degrees. Now we can divide this. We're going to take our 2500 and divide it by 45. From this, we're going to get approximately 56, and then we are given an angle. So for this first part, we divided, and from this next part with our degrees, we are subtracting the top from our bottom. And they're going to have negative 53 minus a negative 27. This is going to give us approximately negative 26. And this would be our answer. However, we need to convert it into our rectangular form. To do this, we are going to do the same thing that we did earlier right here. We are going to have our number out front, which is 56, and then we have the cosine of our angle, which we know to be negative 26, plus the j times the sine of our angle, and then we can just plug this all into a calculator. This is going to give us approximately 50.3 plus j with a negative 24.5. We can write this into our question as 50.3 and then a negative 25. And that's how you would go about solving this problem. First thing we did was this part up here, and that's for our IN, and then the part in green is for our ZT of H. If you have any questions about this problem or the material we covered, you can leave them in the comments below. If you want more intro to circuit analysis or notes that cover the entire coursework, they're below the like button in the description.